Okay, so we've used factors already. We've looked at them, but we want to discuss them in more detail here with more clarity. So remember that factors are basically for um, nominal data, categorical variables, categorical data, qualitative data. So as you've seen, variables can be described as nominal, ordinal, or continuous. Or there are other ways also, numeric, and so on. Nominal variables are categorical without an implied order. So diabetes of type 1 and type 2, that we don't mean that type 1 is less than type 2 or the other way around. There's no relationship in terms of order between type 1 and type 2. Is an example of a nominal variable. Even if type 1 is coded as a 1 and type 2 is coded as a 2 in the data, no order is implied. So we could just call them 1 and 2, but that doesn't mean that we mean that 1 is less than 2. Ordinal variables imply order but not amount. We've talked about this before. So here's an ordinal. Status, there are 3 types, and there is an order here, is a good example of an ordinal variable. You know that a patient with a poor status isn't doing as well as a patient with an improved status, but on the other hand, we don't know by how much. In other words, we can put an order in there, but we don't know like how much difference there is between this one and this one, or this one and this one. So they're not the same as numbers where we would know the difference. For example, if this was a number, if we had a number 2 and a number 5, we would say that 2 is less than 5, but we could also say by how much it's less than 5. But here we can't say by how much this is less than this. Okay? So that's another distinction. Continuous variables can take any value within some range. So continuous variables are like time or age. And both order and amount are implied. Now, he's actually shouldn't use just the word continuous variables, because there are numeric variables. They're not called continuous. For example, just the numbers 1, 2, 3, 4, 5, 6. That's not really called a continuous variable. So he's kind of misusing the word here, but that's okay. We won't worry about that. Age in years is a continuous variable and can take on like either of these values and any value in between. You know that someone who is 15 is 1 year older than someone who's 14, so it's just saying that the difference can be determined. Categorical and nominal, or so-called nominal, and ordered categorical, ordinal variables in R are called factors. So, basically any kind of nominal data, whether it's categorical or ordered categorical, are called factors. Factors are crucial in R because they determine how data will be analyzed and presented visually. You'll see examples of this throughout the book. Okay? Now, sometimes if you have a data frame, I believe that R will convert data to factors automatically sometimes. But you can also use this function to convert something to a factor. And that's what we do here. So here we just have a vector with type 1, type 2, type 1, type 1. And if you use the factor function on this vector, then this is going to be stored differently, stored in R differently. It's going to store it as 1, 2, 1, 1. Now, this 1 has nothing to do with this 1. Just has nothing to do with it. But it's just saying, basically this is saying there's a pattern in this data, and how many different numbers do we see here? Only 2 different numbers. There's only 2 different types in this vector, is what it's saying. And then it's expressing the pattern with these numbers. So it gets stored, actually, when you convert it, when you do this, then whereas before it was stored as strings, now it gets stored just like this, and that makes it faster. Actually, it makes our work on it more quickly when it can store it as a bunch of numbers as opposed to strings. So that's part of the reason why it does it. So what he says is the function factor stores the categorical values as a vector of integers in the range 1 through k. In other words, just numbers, where k is the number of unique values in the nominal variable. So how many unique values are there here? There's only 2, right? So it would be a vector in the range from 1 to 2. So we just have 1s and 2s here. Okay? And an internal vector of character strings mapped to these integers. So when it needs to report back to you, so it stores it like this, but when it needs to report back to you what it is, it has to know that 1 means type 1 and 2 means type 2 and so on. So it has, in addition to storing this, it has an internal vector of character strings, the original values, mapped to these integers so that it can report those back to you if it needs to. The statement diabetes is assigned diabetes with factor stores this vector like this and associates it with like that. Okay, like we said. Any analysis performed on the vector diabetes will treat the variable as nominal and select the statistical methods appropriate for this level of measurement. So, you know, if you apply some function to diabetes or some analysis of the vector diabetes, you know, certain functions will, we've said this before, we called it polymorphism, but anyway, it means just certain functions will behave one way with numeric objects and a different way with non-numeric objects, but so it will know, those functions will know that since you've defined it as a factor, even though it's stored this way, it doesn't, those functions, we don't want the functions to treat it as though it was a numeric vector, because it's not. It's this. It's just stored this way internally so they can act on it more quickly. That's all. But anyway, these special any function that we apply will know that it's a factor and will treat it and will use the appropriate methods for factors as opposed to, and we'll see a little example of this later, but as opposed to treating it as a number. So again, he says any analysis performed on the vector diabetes will treat the variable as nominal and select the statistical methods appropriate for this level of measurement. So level of measurement means, you know, actually measuring things as nominal is sort of not as strong as measuring things numerically. So anyway, it's just he refers to that as a different level of measurement. Or another way, another example would be ordinal variables are not as strong as straight out numeric variables. He also says that you can add the parameter ordered equals true. So you could do this status. It's just a vector like that with characters, but then you could convert it to a factor like this, but you could add this also in there, and then it's going to treat this data or poor, improved, excellent, and poor as ordinal, and so it's going to assign these numbers and associate these values internally as that and this one. Additionally, any analysis performed on this vector will treat the variable as ordinal and select the statistical methods appropriately. Now, why did it work like that? Why did how did it know that it should be that excellent should be 1 and improved should be 2 and poor should be 3? Well, it's kind of silly because the way that it did that was E comes before I and I comes before P. So it just does it alphabetically, which is silly. It's very unlikely that the alphabetical ordering of the first letters has anything to do with what that poor comes before improved and that comes before excellent, or vice versa. So you can change that, though, the alphabetical treatment of it, by doing this. So you do factor, status is the variable, ordered is true, and then yet a third argument is here. Okay? And there you say this will be the lowest, this is the second lowest, and this is the third lowest. Okay? And so now it's ordinal, and the order is correct, right? Poor comes before improved, and improved comes before excellent. Okay? So then you don't have to worry about whether P how P is related to I is related to E. Be sure that the specified levels match your actual data values. Any data values not in the list will be set to missing. So don't forget that, get all of your values in there. If you leave out one of them, then it's going to get confused, and it'll call them if anytime it sees. For example, suppose I forgot to put improved in this list here, so I only had these 2. Then anytime it sees improved, it's just going to set that to missing in the actual data set. Okay, so let's stop this one, and then we'll look at this example.